Good morning, good afternoon, good evening. This is Lecture 13 Multi-Agent Reinforcement Learning. This is your Professor T. Freed Mohammed, PhD AI 830, University of Cumberland's sequence of lectures. Multi-agent reinforcement learning is a study of what happens when multiple learning agents share the same environment, each pursuing its own objectives, while influencing every other agent's experience through its actions. This is fundamentally different from single agent settings we have studied so far. Because the environment is no longer a passive backdrop, it is actively shaped by the decisions of all agents simultaneously, making the learning problem significantly more complex. The team behind AlphaStar, DeepMind's StarCraft 2 playing system confronted exactly this complexity. The game requires one agent to control dozens of military units across the map, coordinating attacks, managing resources, and responding to an opponent who is also learning and adapting in real time. Building a system that could handle that level of simultaneous interactions, where every unit's action affects the global state and the opponent's strategy changes the optimal response at every moment, required the full machinery of multiple agent learning or multi-agent learning, and the result became one of the landmark demonstrations of what this field can achieve. So today's lecture is structured around the four problems that define multi-agent reinforcement learning as a discipline distinct from single-agent methods. We begin with the foundational concept, what it means for multiple agents to learn in a shared environment, before examining the four central challenges that raise as soon as you add a second agent to the system. The environment becomes non-stationary. Agents must somehow coordinate their actions. They may need to communicate, and attributing individual credit from a shared team outcome becomes genuinely difficult. The second half covers the three main architectural frameworks researchers have developed to address these challenges, followed by a survey of real-world domain where these ideas are being deployed. The progression mirrors how the research community itself has historically tackled MARL. First, understanding why it is hard, then developing principled solutions, and finally validating those solutions on real problems of increasing scale and complexity. Introduction to MARL, multiple agents learning simultaneously in a shared environment. The introduction to multi-agent reinforcement learning requires resetting some institutions in terms of learning. In reality, the intuitions build up through single agent study. So the one institution is single agent study. Several institutions, there are several agents working in tandem. In single agent reinforcement learning, we assume the environment obeys fixed rules that do not depend on the agent's policy. The physics of a game, the dynamics of a robot's joints, the rule of a maze in MARL. This assumption breaks immediately the moment a second agent enters the environment. The effective dynamics that any one agent experiences depends on what the other agent is doing, and that changes as both agents learn. A warehouse automation company deploying a fleet of autonomous forklifts discovered this concurrently when they initially treated each forklift as an independent single agent system. Each vehicle learned to navigate effectively in terms of efficiency in isolation during testing, but when all vehicles were deployed together, their individually optimal paths created congestion and deadlock at intersections. Behaviors that never appeared in single agent testing precisely because the presence of other learning agents fundamentally changed the environment each forklift was navigating. The core insight of MARL is that an agent's optimal policy cannot be determined independently of what other agents do, because the state of the world that each agent observed at any moment in the joint result of every agent's preceding actions. This circular dependency may best action in terms of, let's say, my best action depends on your action as a human way, and your best action depends on mine, is what makes MARL a qualitatively different problem from single agent optimization, not merely a scaled up version of it. When Waymo began scaling their autonomous driving research to intersections involving multiple self driving vehicles, they encountered this dependency directly. A vehicle's optimal merging strategy depended on whether the vehicles around it were also self driving agents with predictable learned policies on human drivers with highly variable behavior. Training policies that assumed a fixed distribution of other drivers' behavior produced agents that performed well in training but failed to adapt when the composition of other agents around them changed, demonstrating that in a world of multiple learners, the behavior of each agent is inseparable from the behavior of all others. The comparison between single agent and multi agent reinforcement learning is most clearly understood through the concept of stationarity. In single agent RL or reinforcement learning, the environment transitions from one state to another according to the fixed rules. So, this is very important and a profound way to understand the MARL concepts, the rules of physics or the coded logic of a game. And the agent's task is to find the best policy given those fixed rules. In multi-agent reinforcement learning, the effective transition rules that any one agent experiences change continuously as the other agents update their policies, which means the optimization target keeps moving throughout training. The diagram captures what makes multi-agent learning structurally different from the single-agent case. The shared environment sits at the center, and every agent feeds its action into the central entity at every time step, receiving a reward and an observation in return. The critical features the critical feature is that the next state of the environment, what every agent will observe on the following step, is determined by the combination of all agents' actions simultaneously, not by any one agent's action alone. A team developing traffic signal control a mid-sized city used exactly the structure. Each traffic light has modeled as an individual agent that observed the queue lengths on its own roads and chose a signal phase. While the shared environment, the road network, evolved based on the combined phase decisions of all lights simultaneously. When agents are trained with awareness of this joint effect, they developed a coordinated green wave pattern that reduced average vehicle wait time across the city, an emergent behavior that arose purely from multi-agent interaction structure and was impossible for any individually trained signal controller to achieve. The four challenges covered in this section, non-stationarity, coordination, communication, and credit assignment, are not independent problems but interconnected faces on same underlying difficulty. Non-stationarity in multi-agent systems means that statistical patterns an agent observes in its environment data are not constant across training time because those patterns depend on other agents' policies which are simultaneously being updated. From a theoretical perspective, this violates a foundational assumption of standard reinforcement learning. Convergence proves that the environment's transition probabilities are fixed. From a practical perspective, it means that the transition stored in an agent's experience buffer from early in training when other agents had different policies may be actively misleading when replayed later because the same state and action pair would now produce a different outcome. A team training cooperative agents to manage power grid load balancing found that standard independent Q learning consistently produced oscillating policies. One agent would learn to shift load to a particular time slot, the second agent would adapt to do the same, which would overload that slot, causing the first agent to shift away again. A cycle that continued indefinitely without convergence because each agent's learning was continuously destabilizing the environment the other was trying to learn in. Coordination failures coordination failure is a phenomenon where individually rational learning agents converge to a joint outcome that is collectively suboptimal, even when a better joint outcome exists and all agents would prefer it. This happens because reaching the better outcome requires agents to simultaneously adopt complementary strategies, and gradient based learning provides no guarantee that agents will synchronize their policy updates in the right way. The concept of a Nash equilibrium from game theory describes the stable points of this process. A joint policy where no individual agent can improve its own reward by changing its own action while others keep theirs fixed. The problem is that multiple Nash equilibria often exist, some better than others, and independent gradient based learners may settle in a poor one. The company developing multi agent negotiation systems for B2B procurement found this directly. Two learning agents negotiating over price and delivery terms would often converge to an inefficient equilibrium where both were slightly dissatisfied even though a Pareto better agreement, one would have made both agents better off, existed and was reachable, but only if both agents simultaneously shifted strategy in a coordinated direction that individual gradient steps never produced. Communication in multi-agent systems is the mechanism through which agents share information that is not directly observable from the environment, reducing the uncertainty each agent faces about other agents' intentions and current states. Explicit communication means agents transmit learned, vector valued messages through a dedicated channel, and both the content of the messages and the interpretation of received messages are trained jointly with the policy. The agents learn what to say and how to listen at the same time. So, this is I would strongly suggest you to look at the explicit and implicit communication between the agents in more depth. Conduct a study user use the Google Scholar or IEEE Explore to find what other people have been discussing this specific way of communication, because this allows you to learn more in depth of the other people, how they are working with both explicit and implicit communications between the agents. Let me share with you an example. A team building a cooperative search and rescue drone system found that explicit communication between drones dramatically improved coverage efficiency without communication. Drones frequently searched the same areas because each could only observe its local neighborhood. When drones were given a learned communication channel through which they could broadcast their current target location to teammates, they spontaneously developed an a coverage protocol without being explicitly programmed to do so, where each drone broadcast caused its teammates to avoid nearby areas, resulting in systematic area coverage that emerged purely from the end to end training of the communication policy. The credit assignment problem in multi agent systems asks a question that has no clean answer in the general case. When a team of agents produces a joint outcome, winning a game, completing a task, earning a collective reward, how much of that outcome should be attributed to each individual agent's specific action? In the simplest cooperative setting, every agent receives the full team reward regardless of its individual contribution, which means an agent that did nothing useful receives the same training signal as one whose action was decisive. A team reward equals the sum of all individual contribution signals, but each agent only controlled its own action. This mismatch is the credit assignment problem stated precisely. A company training multi-agent system to optimize warehouse picking routes encountered this directly. When the system succeeded in meeting the delivery deadline, the team reward was shared equally among all picker agents, including those that had taken inefficient paths that were compensated for the other agent's efficiency. Without a mechanism to isolate individual contribution, specifically without asking what would the team outcome have been if this again agent had taken its average action instead of this one. Agents had almost no gradient signal to improve their individual behavior, and training stagnated despite the team eventually finding a workable joint strategy through random exploration. The three learning frameworks covered in this section are independent learning, centralized training with decentralized execution, and joint policy learning. So, how to structure training when multiple agents are learning at once? Independent learning is the baseline approach that every multi agent research project should evaluate first before investing in more sophisticated methods. Take any standard single agent algorithm, DQN, PPO, actor critique. Give a copy to each agent and let them train simultaneously without sharing any information. The appeal is obvious. No architectural changes are needed. Existing single agent codebases work without modification, and the system scales trivially by adding more agent processes. The limitation is equally fundamental. From each agent's perspective, the environment appears non stationary because other agents are changing their policies and any experience stored in an agent's replay buffer becomes progressively stale as a result. Centralized training with decentralized execution, CTDE, is built on practical insights about the differences between what is available during training and what is available during real world deployment. During training, which happens in simulation, we can give a shared critique access to the full global state, all agents' positions, all agent actions, or agents' actions, all agents' observations. Because this information exists inside the simulator and can be freely accessed. During deployment, each physical agent can only observe what its own sensors can see. CTDE exploits this asymmetry, use the rich goal information in terms of global information during training to produce better gradient estimates for each agent's actor, then deploy only the actors, each of which operates entirely on its local observation or on its own local observation. Joint learning treats the entire team of agents as a single decision-making entity whose action at each time step is the combination of all individual agents' actions taken together. The joint policy maps from the current world state to this combined action tuple, and it is trained to maximize the expected team reward just as a single agent policy would be trained to maximize its own reward. The shared critique multiple actor architecture is the most widely deployed implementation of the centralized training with decentralized execution framework. The critique is a single neural network that takes the full global state concentrated with all agents actions as input in the produce and produces a joint value estimate, essentially asking, given the entire team is in this global configuration and took these actions, how good was this step for the team overall. The actor networks, one per agent, are much simpler. Each takes only the agent's own local observation as input and outputs as a probability distribution over its own action space. Parameter sharing means that all agents in a system use the same neural network weights rather than each maintaining a separate independently trained network. When an agent takes an action and receives a reward, the gradient updates that the result is applied to the one shared network, which every agent then reads from. The applications section grounds everything discussed so far in concrete domains where multi-agent reinforcement learning is not a theoretical exercise but an engineering requirement. Multi-agent reinforcement learning has moved from academic benchmarks to production systems across domains as different as hospital management, financial markets, and competitive game AI and robotics. Fleets of autonomous mobile robots in Amazon and Ocado warehouses coordinate item retrieval using learned multiple or multi-agent policies that adapt to changing inventory layouts and variable numbers of active robots on the floor at any given time. The deepest insight in multi-agent reinforcement learning is that the interaction between agents is not a complication to be managed but fundamental phenomenon being studied. An agent learning is a multi-agent in a multi-agent environment is not just learning about the physical world, it is learning about strategies of other agents, adapting to those strategies and simultaneously causing those agents to adapt to it. This makes MARL a moving target in a simultaneously causing those agents to adopt it in a precise sense. The optimal policy at any moment depends on the current policies of all other agents, which are themselves moving targets. The six takeaways from this lecture form a structured picture of what multi agent reinforcement learning is, why it is difficult, and what the current state of practice looks like. So, I strongly suggest you to conduct more research in this area because this is an area which is going to be the multifaceted AI vertical firms will be using or have started using already. See you in the next lecture.